Okay, here is another unique problem where there's a series parallel AC circuit with two current sources. But very importantly, this is more of a parallel circuit than a series circuit. And very important as well, these are current sources. They are not voltage sources or a current source and a voltage source. They are both current sources. Why am I saying this? Well, you may think like, okay, this is simple, we can just apply the same method for all of them. But no, this is more of a unique rule because again, this is a parallel circuit. All the components can be made in parallel. They are not having any other restraints. Okay, and because they're current sources, they are also a lot easier to calculate compared to voltage sources. And I choose this problem to do with you as well because I would like to show it to you as an example that some circuits like this one, it doesn't need a complicated network theorem to apply to it. You can simply use not really common sense, but kind of like a simple way of solving it. Okay, so let's get started. Oh yeah, and what's asking us is to find the current and the voltage. Basically, we have to find the the voltage in this resistor here in R2, no R3, with this 12k ohms, and the current will be the current here that goes like right at middle here. And how do you tackle a problem like this? Because you know it looks very complicated. It's got a lot of components in parallel. It's got two sources. It's got a capacitor in here as well. So how do you do it? Well, we start with the basics, and that is because these two are in parallel. You can actually make these two sources in only one source. And how do you do that? Well, you can say that IT, the total current, will be equal with, let's call this one I1 and let's call this one I2. This one I1, so let's say I1, this one I2. And the way you do it is that this current goes in the up direction, this current goes in the down direction. So you can see that they are already opposites. So let's make I2 the negative value, minus I2, and I1 stays as a positive value. Because they go in different directions, at least one of them has to be a negative. So then that will be equal with, sorry, I'm going to sneeze. Cheers. Okay, so now what we do, we can do 12 milliamps at an angle of 40 degrees minus 8 milliamps at an angle of 0 degrees. All right, and to do this calculation, we just simply need to do x, it's equal with 12 cos 40 degrees, that will be equal with 9.2 times 10 to the minus 3. Remember, we are using milli values here. This is a milli. And then y is equal with 12 milliamp sine 40 degrees. That will be equal with 7.7 times 10 to the minus 3. So then IT will be equal with 9.2 times 10 to the minus 3 plus J, let's see, 7.7 times 10 to the minus 3. Alright, and then we just take it away by the simple value of 8 milliamps, so it will be minus 8 m times 10 to the minus 3 without any J value because there's no J value here, there's no phase. So then that one, IT, will be equal with, I have it written down here, so it will be equal with 1.2 times 10 to the minus 3 plus 7.7 times 10 to the minus 3. Alright, actually I can just calculate it because it's 8 and 9.2, but never mind. Okay, so now we need to make it the z value, so z value will be equal with square root 1.2 squared plus 7.7 squared. This is milli again, so mm, and that will be equal with, I really need to get some better pages because I really don't like them. That's equal to 7.8 times 10 to the minus 3. Alright, now we are going to go to the next one, which will be this one. We need to calculate the angle. Let me write a bit bigger, so that'll be 10 minus 1, so maybe this is a lot clearer. And that's equal to 7.7 times 10 to the minus 3 over 1.2 times 10 to the minus 3 That'll be equal with 81.14 degrees. So therefore IT will be equal with 7.8 milliamps. Maybe it's a bit clearer if I write bigger with more space between them. 81.14 degrees. It's not like I don't have enough pages. Okay, so then we got the total current. Now let's calculate the resistances, the Z values. And this is actually very interesting. We can combine all three together in only one component and just make IT total and one component together, you know. But we need this current specifically going through these two components. So what we can do is we can combine R1 and R3 together in one component, because you'll have the same voltage anyway later on because they're all in parallel, and then just get these two in series and see them as one component as well. So what we can say is that, and I'll show you in a second what I mean by it, we can say Z1 is equal with R1 and R3, and those will be equal with 4K in parallel with 12K. They are both resistors, so they have the same phase. There will simply be 3K at an angle of 0 degrees. And then we can say that Z2 is equal with ZR2 and XC, and they are in series components. So there's and because it's a capacitor, so it will simply be, let's see here, there'll be 20K minus J 40K. All right. The next step will be to convert this one into polar form. So Z will be equal with square root 20K squared plus 40K squared. That one will be equal with 44.72K. And then the angle will be equal with 10 minus 1 minus 40K over 20K. And that will be equal with minus 63.43 degrees. All right. So we got this value. So we can say that Z2, it will be equal with 44.72K at an angle of minus 63.43 degrees. Okay, so we can see it. So what do we do with these values? Well, why would you say like instead of ZR1, ZR2, it's Z1 and Z1 and Z2, it's like ZR2 and XC. Well, we can like convert all of these in a new circuit that's a lot easier to understand, which will look something like this. So that'll be the IT, that'll have 7.8 milliamps at an angle of 81.14 degrees. And there will be two components. This one will be Z1 at 3K and a phase of 0 degrees, and this component, it will be Z2. And the way I use this rectangle, see the name inside of them, is because you can't really assign a component to it. I mean, like, I guess you can say this will represent a capacitor, but when you do the calculation, that won't be very fitting, you know. You don't use really the properties of a capacitor, so you simply like, I simply like to put them as a rectangular and use it like that at an angle of minus 63.43 degrees. And this is the current that we need to find out. And remember that they are all in parallel, so all will share the same voltage. So then we can also find the voltage inside the 12K ohm resistor because they are all in parallel, as seen in this diagram here. Okay. So we can just apply the simple rule like the current split rule. So then I will be equal with Z1 divided by I over Z1 plus Z2. And that will be equal with 3K times 7.8 milliamps at an angle of 81.14 degrees over 3K at an angle of 0 degrees plus 44.72K at an angle of minus 63.43 degrees. and then that one will be equal with 23.4 at an angle of 81.14 degrees over 3k plus 20k minus j 40k, and this will be equal with 23.4 at an angle of 81.14 degrees over 23k minus j 40k. Alright, now what we need to do is to convert these numbers. So I guess we can put like this. So then z is equal with square root 23k squared plus 40k squared. That will be equal with 46.14k. And then the angle will be equal with tan minus 1. It's got the minus value here. That will be 40k over 23k. And that will give us a nice number of minus 60 degrees. Alright, so we convert them. So now we can say that I, it's equal with 23.4 at an angle of 81.14 degrees divided by 46.14 at an angle of minus 60 degrees. And the answer will be 0.51 milliamps at an angle of 141.14 degrees. Okay, now let's go to the next one, which will be to find the voltage. And again, the voltage is really easy to find. We can pick any of them. We can even use Z1, but we don't know the current for Z1, so we're going to use Z2 again. So the voltage V will be equal with I multiplied by Z2, which is equal with 0.51 milliamps at an angle of 141.14. Let me like put it a bit higher so you can see better. There you go. Degrees times 44.72k at an angle of minus 63.43 degrees. And this will be equal with 22.81 volts at an angle of 77.71 degrees. And there you have it. We even made such a complicated problem like this one that has multiple resistors and one capacitor with even two current sources into this simple problem, into this simple circuit with only one current source in one direction and just two components that have their own resistance and phase. But again, remember, this works because it's a special situation. It doesn't always work like this. You can't always use it like that. The reason it works is because they're in parallel, and it's also because, yeah, there's a big reason. Or maybe like it works to most of them. To be honest, I didn't really study network theorem too much. I just know this is like one of the examples that you can apply to like normal series parallel circuits. But maybe in network theorem it will be simple like this, but I really doubt that, especially since we use complex numbers. Surely it's a trick to it. But anyway, okay, let's go to the next exercise. Don't worry, we got only 2 more problems, and after those 2 more problems we are going to be done with this video. You are going to fully understand how to calculate series parallel AC circuits that have more of a complicated design like this one here. Alright, so these 2 pages are full, so I'm done with these 2 as well. Okay, this is the next one, the series parallel AC circuit, and this one, yeah, it does have only one voltage source, but it's a lot more complicated since we got 3 resistors, 1, 2, 3 here, 3 resistors. We also got 2 inductors, one here, and we also got 1 capacitor here. And you may look at this one, you may be like, well, this is already very complicated. And not only that, but in this one we need to find currents. So I need to find the current I1 going to the resistor one, we need to find the current I2 going through R1 and XL1, and we need to find current 3 going through R3, XL2 and XC. So let's start with the basics. First, let's convert all of these values into Z values. And even better, let's convert them depending on the current. Let's split the circuit. So we want to know this current here, yes. So then let's make this one its own special Z value. So this current I1 goes through only one component. So Z1 will be equal with R1, which will be equal with 20 ohms at an angle of 0 degrees. Alright, let's go to the next one now, which will be this one, I2. So Z2 is equal with, and through I2, what components that goes through it? Well, the resistor goes through it, and the inductor goes through it, and then it will go through the ground. So then it will be R2 plus JXL. And this one will be equal with 6 plus J8. Alright, now let's go to the current number T. So what components goes through current number T? Well, current number T goes through resistor 3. The current also goes through XL2 and it goes to XC. So then Z3, the third Z value that we split it in, will be R3, this resistor here, plus XL2, so JXL2, minus the capacitor, which is BJXC. And that will be equal with 16 plus J6 minus J18. Remember, we can do this because they are in series. These three components are in series, and these two components are in series. That's why we are simply allowed to add them together to get the values. If they were in parallel, then it will be a bit more complicated. Let's say there's one more in parallel here, then yes, we need to add another Z value, Z4 value for the parallel component in here because it will affect the current. But yeah, we can write it as like this, and we can simplify the circuit again. Instead of having so many complex components, we can just say that there is a source, which will be E equal 300 volts at an angle of 0 degrees, and we can say there's one rectangular here, there's one rectangle here, and there is one rectangle here, and the values will be Z1, that will be 20 ohms, 0 degrees, which will be this one. You can say this one Z2, and Z2 has 6 plus J8, and Z3, which Z3 has this one, which is 16 minus J12. We can also write it in polar form, but we are going to convert it in polar form anyway. Okay, so yeah, these are the Z values. So we simplify this complex circuit into a simple parallel circuit like this one with 3 components. And again, to find the total current, which will be I, this one will be I1, this one will be I2, and this one will be I3. To find the total current, first we need to find the total Z values. And the total Z values, because they are in parallel, it will be the parallel values. But first we need to convert it in polar, so that will be Z will be equal with square root 6 squared plus 8 squared. That will be obviously equal to 10 squared, and then angle of 10 to minus 1, that will be 8 over 6, that will be equal to 53.13 degrees, like usual. This will be for Z2. For Z3, it will be equal with square root, that will be 16 squared plus 12 squared, which will be equal with 20, and an angle of 10 to minus 1, 12 over 16, that will be minus 36.87 degrees. Alright, so we have the polar forms as well. So now we can calculate the total ZT value. So ZT will be equal with, there you go, 1 over Z1 plus 1 over Z2 plus 1 over Z3. And then that one will be equal with 1 over 20 angle of 0 degrees plus 1 over 10 and then angle of 53.13 degrees, and then plus 1 over 20 minus angle minus 36.87 degrees. Sorry for the writing, but you already know how to calculate the total, I imagine. So you do that one over them, so then that will be equal with 1 over, that will be 0.05 angle 0 degrees plus 0.1 angle of 53.13 degrees plus let's say 0.05 at an angle of minus 36.87. Don't forget to reverse polarity, so this one becomes a minus, this one becomes a plus. Alright, now we need to calculate the x and y values, so x will be equal with 0.1 cosine minus 53.13, that will be equal with 0.06, y will be equal to 0.1 sine minus 53.13, that will be equal with minus 0.08. X will be equal with 0.05 cosine 36.87, that will be equal with 0.04. And y will be equal with 0.05 sine 36.87, and that will be equal with 0.03. Alright, let me put this on a bit higher so you can see. Alright, so now we converted them, so we can say that zt will be equal with 1 over all of those values, 0.05 plus 0.06 minus j 0.08 plus 0.04 plus j 0.03. Okay, and then that one will be equal with 1 over 0.15 and minus j 0.05. Now we convert it back to polar, so z is equal with square root 0.15 squared plus 0.05 squared, that's equal to 0.158, and then the tan is equal with angle is equal to 10 minus 1 minus 0.05 over 0.15, and that's equal with minus 18.53, right? And then zt will be equal with 1 over 0.158 at an angle of minus 18.53, and this one will be simply be equal with, so 1 over 0.1 this number, that will be 6.32 at an angle of 18.43 degrees, because again, remember, when you do the division, you reverse the sign. Alright, and you reverse it because this is basically like angle of 0 degrees, and minus with minus, that makes it plus, that's why you always reverse it. But anyway, so we don't have any more space on this page, but we find the total zt value. Now the only thing left is to find the current I1, the current I2, and the current I3. And also we are going to check with the total current to see if we get the right answer, just to make sure. So I have here more space on the other side of the page, and this one we keep going. So then the total current I will be equal with E over zt, that will be equal with 300, the angle of 0 degrees, divided by 6.32 at an angle of 18.43 degrees, and that one will be equal with 47.47 amps, an angle of minus 18.43 degrees. I1 will be equal with E Z1, that is equal with 300, an angle of 0 degrees, over over 20 at an angle of 0 degrees, because that's the first Z value here. See, this Z here, 20 at an angle of 0 degrees, and then that one will be equal with 15 amps at an angle of 0 degrees. So just be kind of going through it. I2 will be equal with E over the value of Z2, and the value of Z2, if the value of E is 300 at an angle of 0 degrees, value of Z2, that was 10 at an angle of 53.13, and that's equal with 30 amps at an angle of minus 53.13. Remember, the angle reverses. And now I3, which is the last one, it's equal with E divided by Z3, that's equal with 300 at an angle of 0 degrees, divided by 20 at an angle of minus 36.87. Angle again reverses, that will be 15 at an angle of 36.87 degrees. So you can see, like this one, the total current wasn't really didn't affect these three values. So because we know the total current and we know these three values, we can actually just check to see if they match. And if they match, that means our calculations were correct. So IT is equal with I1 plus I2 plus I3. That's equal with 15 at an angle of 0 degrees plus 30 at an angle of minus 53.13 degrees, and then plus just a bit 15 at an angle of 36.87 degrees. Okay, so then the x values will be equal to 30 cos minus 53.13. I start running out of ink, I think. That's 18. Y is equal to 30 sine minus 53.13. That's equal to minus 24. X is equal to minus 15 cos 36.87. That's equal with 12. And y is equal with 15 sine 36.87, and that's equal with 9. So IT would be equal with 15 plus 18 minus J24 plus 12 plus J9, and that's equal with 45 minus J15. So Z would be equal with square root 45 squared plus 15 squared, and that's equal with 47.44. And then the angle is equal with 10 to the minus 1, and that's minus 15 to 45, that's equal with minus 18.43. So then IT will be equal with 47.44 and an angle of minus 18.43 degrees. Alright, so this is our answer. That will be we can see that they are exactly the same numbers. Well, almost exactly. This one is 47.47, this one is 47.44, but the angle is exactly the same. And let me circle them. So the angle is exactly the same. It's only a difference of 0.03 in here and here. So I'll say this is pretty accurate, so I'll consider my answer correct, even though it's such a small difference. Again, this is because we don't like always round the numbers properly. We don't use all the decimal values. If you use all the decimal values, then yes, you'll always get the perfect answer, but you don't always get the perfect answer, unfortunately. Anyway, okay, let's keep going because there is only one more left and then we are finished. So the last one left will be this one here, which is already a lot simpler than the previous one. It may seem, but actually there is still a lot to calculate, because this one is not all of it in parallel. As you can see, the current goes through this resistor, and then it splits in two currents, I1 and I2, that goes through these resistors. Okay, again we are going to use the same method that we used before, and that will be to just give me a second, like I don't know, I'm taking this one in one straight recording, and yeah, I do breaks to drink water, but those breaks it's only a few seconds long, and I've been like writing for like 2 hours I think by now. So yeah, and it like my fingers kind of start hurting, but this is the last problem, so we are going to do this last push. Well, I'm going to do it, you're just watching. So again, we apply the same method like we applied to the previous one. So what current goes through I total? No, through what components goes the current? So it goes through R1 and it splits in two. So I can say that Z1 is equal with R1, and that will be equal with 8 ohms and an angle of 0 degrees. And then we can say that Z2 is equal with, so let's say this is current here, but it goes through R2 and it goes through XL. So you can say that Z2 is equal with R2 minus XC. Remember, be careful on the currents. Like you can couple them together if they are in series with the same current, but if they have different currents, for example like this one, I can couple Z1 with anything else because it just splits. So as long as it doesn't split, you can couple it with as many components as you want. So that one will be equal with 18 ohms minus J14 ohms. And then Z3 is equal with, in Z3 the current 2 will go through the XL, the inductor, and will go to the resistor, so it will be like XL plus R3, and that one will be equal with 16 plus J12. I'm not going to put it all the other way around because I have to make it 100 times more confusing. Anyway, now Z2 will be equal with, we need to make it in polar form, so that'll be 18 squared plus 14 squared. That's equal with 22.8. Angle, which is equal with 10 d minus 1 minus 14 over 18, again because it's negative value. That's equal to minus 37.87. Z3 is equal with square root 16 squared plus 12 squared, which is equal to 20, and the angle is equal to 10 minus 1, which is equal with 12 over 16, that's equal with 36.87. Okay, so Z2, Z3. So then Z2, it's equal with 22.8 at an angle of minus 37.87. And then Z3, it's equal with 20 at an angle of 36.87. Strange, it's like quite a difference, almost 180 degrees difference perfectly. But anyway, so let's keep going. So we can redraw the diagram again, as this is the source. E is equal with 150 volts. I'm rushing it because I have like 20% left. So after 5% battery, it will turn off the flashlight, which will be a bit more quality. So Z1, then another rectangular here for Z2, then another rectangular here for Z3. Remember, this rectangular here, Z1, it's connected like this because it goes through only this resistor here. So that'll be 8 ohm at an angle of 0 degrees. Let me connect these two together. That will be 22.8 at an angle of minus 37.87. And this one here will be 20 at an angle of 36.87 degrees. This one will be I1 and this one will be I2. So now that it's like organized, and we can call this one, the total will be Z2 and Z3. You'll see later why. So now that everything gets organized, we can calculate the total resistance. But because we can, they aren't like all in parallel or all in series, first we need to calculate this section here to make and to know the value. So then Z, the Z2 and Z3, that'll be equal with 1 over 22.8 at an angle of minus 37.87 plus 1 over 20 at an angle of 36.87. Okay, and this will be equal with 1 over 0.044, reverse the angle to 37.87 plus 0.05, again reverse the angle to minus 36.87. We need to calculate we need to make it in rectangular form, so x is equal to 0.044 cosine 37.87, which is equal with 0.035, and y is equal with 0.044 sine 37.87, that's equal with 0.027. X is equal with 0.05 cos minus 36.87, and that's equal with 0.04, and y is equal with 0.05 sine minus 36.87, and that times equal with minus 0.03. All right, now Z2 and Z3, that will be equal with 1 over 0.035 plus J 0.027 plus 0.04 minus J 0.03. Let me there you go, you can see better now. All right, and then these values, they will be equal with 1 over 0.075 minus J 0.003. All right, now the next one will be Z will be equal with square root 0.075 squared plus 0.003 squared. That will be equal with 0.075. The angle will be equal with 10 d the minus 1. Negative value 0.003 because j is negative over 0.075. That's equal with an angle of minus 2.3 degrees. Alright, so then z, the total z2 and z3, so those two components, they'll be equal with 1 over 0.075 angle of minus 2.3 degrees, so they are equal with 13.33 at an angle of 2.3 degrees. Alright, so we find out the total resistance between the total z value between these two, so they become one z component, zt, z3, so then they will become in series. So now we can just add them with z1. So then z total will be equal with z1 plus t z2 and z3. That will be equal with 8 plus 13.33 at an angle of 2.3, and that will be equal with 21.33 at an angle of 2.3 degrees. Alright, so that will be the total. Now we need to calculate the current, the total current I, which will be equal with E over ZT, that will be equal with 150 angle of 0 degrees over 21.33 at an angle of 2.3 degrees. That will be equal to 7.03 amps at an angle of minus 2.3 degrees. Now we can calculate the total power as well, which will be equal with E times I times cos angle t. I think I forgot to write it there, that we calculate the power, but I calculate it anyway. So 150 times 7.03 times cosine of 2.3, that's equal with 1053.66 watts. Alright, next one will be I2. I2 will be equal with, and we can split, can do a split current, so that'll be Z2 multiplied by I over Z2 plus Z3. Okay, and then that will be equal with 22.8 at an angle of minus 37.87 multiplied by 7.03 at an angle of minus 2.3. Okay, and all of it together be 22.8 at an angle of minus 37.87 plus 20 at an angle of 36.87. Alright, so now we can simplify this even further. We can say it's 160.28, and there you go, it went off. Okay, now you can see my shadow at an angle of minus 40.17 over 18 minus j14 plus 16 plus j12. That will be equal with 160.28 at an angle of minus 40.17 over 34 minus j2. Alright, let's slow it down because this is towards the end anyway. So then the angle will be square root 34 squared plus 2 squared. That's equal with 34.06. Angle is equal to 10 to the minus 1. That's equal to minus 2 over 34. That's equal to minus 3.37. Okay. I2 therefore will be equal with 160.28 with an angle of minus 40.17 over 34.06 at an angle of minus 3.37. That will be equal with 4.71 at an angle of minus 36.8 degrees. So we found the current I2, which will be the current going through here. Now we just need to find the current I1. So the current I1 will be equal with Z3, which is the opposite one, multiplied by the current times I over, again, Z2 plus Z3. So this one stays the same, so it make it a lot easier. There will be 20 at an angle of 36.87 multiplied by 7.03 at an angle of minus 2.3 over 34.06 at an angle of minus 3.37, and this will be equal with 140.6 at an angle of 34.57 all over 34.06 at an angle of minus 3.37. So therefore I1 will be equal with 4.128 an angle of 38. And there we have it. We got the total power, we got the current I1, and we got the current I2 through these two circuits. Okay, sorry for like towards the end that the flashlight went off. Again, it's because I don't have enough battery anymore. But don't worry, we finished everything is done. I'm not going to like do an outro, like a long one. That's it. This one was like one of the hardest ones to record because I didn't have a break in between or anything like that, like a proper break, like an hour break or anything like that. So thank you again for watching. If you have any questions, just put it in the comments below, and I hope you can understand what I'm writing here. Again, I'll try to like find better pages again because I don't like you can see through this one and it's a bit confusing sometimes, but yeah. Anyway, thank you for watching, and I'll see you next video with like network theorem, or maybe like circuit theorem, basically like methods to calculate them, like node analysis or superposition. All right, bye.